Michael Faraday also had a very important discovery in the field of electromagnetism, and we're going to talk about that here. So not only did he see that essentially come up with the motor principle, but he also found that you can induce an electric current with a magnetic field as well. So when Ørsted demonstrated the ability of a steady current to produce a steady magnetic field, scientists assumed that a steady magnetic field would produce a steady current. It seemed logical, but it didn't work that way. In 1831, though, Michael Faraday discovered the basic principle of electromagnetic induction. Faraday made his discovery by experimenting with conductors in the vicinity of magnetic fields. He found 3 different scenarios where he can generate this, where he can induce this current. The first was moving the wire through the jaws of a horseshoe magnet. So as the wire was moving, current would flow, but only when it was moving, not when it was stationary. The second was if he dropped a bar magnet through a coil of a conductor. And if this happened, if the magnet was moving, current would flow. And the third was if he touched the iron core of a coil with a bar magnet. So in this case, Faraday found that electric current was only observed in the coil when the iron core was being magnetized or demagnetized. So this gave us the law of electromagnetic induction. Any change in the magnetic field near a conductor induces a voltage in the conductor, which induces an electric current in the conductor. So if we have a changing magnetic field, either through the process of magnetism or demagnetism, or through the physical process of the conductor moving through the magnetic field, or a magnetic field moving in the presence of a stationary conductor, anything like that would induce an electric current. This is our law of electromagnetic induction. This diagram shows a loop of wire inside a uniform magnetic field, so a circular loop of wire in this field. Which of the following will produce an induced current in the loop? If we move the wire up and down in that field, it's not cutting any of those magnetic field lines, so no current would be induced in that case. But if we move it left and right, it's now cutting the magnetic field line, so we would have a current induced in the wire. If we rotate it, it's also cutting those field lines, so we would also have a magnetic field induced. If we compress the loop, if we make it smaller, it's cutting through magnetic field lines again, so we do have, again, an electric current induced. So Faraday came up with what was really the first transformer, this iron ring. So Faraday's iron ring was used to induce a current in one circuit and use that current to, have a current flow in one circuit and use that current to magnetize a soft iron core ring, which would then induce a current in the second coil. So this is his device, the iron ring. When the switch was turned on, there would be current flowing through here. This would magnetize this core, which would give a magnetic field, and as that was being magnetized, it would cause current to flow in that secondary loop. So you can copy this down for Faraday's iron ring. The primary coil is connected to a voltage source. The secondary coil is connected to a galvanometer. A galvanometer is an old type of ammeter, so it's just used to measure amperage. And again here, it's going to go through what I just said. When the switch is closed, the current in the primary circuit causes the entire ring to be magnetized. The sudden increase in the magnetic field strength from 0 to some non-zero value induces a current in the second coil. However, once the magnetic field in the iron ring is stable, there's no longer a changing magnetic field, so the induced current no longer exists. When the switch is opened, the electric current stops flowing and the magnetic field in the soft iron ring collapses from maximum strength to 0, and that causes current to flow in the opposite direction on the secondary coil. And again, we have no current when the iron ring is now back at 0 in terms of its magnetized state. So what are the factors affecting electromagnetic induction? The number of turns on the induction coil, the rate of change of the magnetic field, so if we can have a magnetic field changing at a faster rate, and the strength of the induced magnetic field. So the stronger the magnetic field, the stronger the current induced. So you can write these down, the factors affecting electromagnetic induction. So in applications of induction, there are induction stoves now. They don't use this type of heating coil that you see here, but what they actually do is they induce a current in your cookware itself. And by inducing a current in that cookware, then you can heat up the pot or the pan, and that can heat the food. And this is actually better for the environment and a better way of cooking, because less thermal energy is lost to the environment. So not like a gas stove where you have a lot of heat coming off the sides, or an electric stove where we have another source of a lot of heat and light being used up. Here we try to directly heat the pot or the pan in order to cook. It actually is a bit safer because now you can the surface of the induction cooking surface tends to get colder faster, so it is a bit safer in that sense too. You can't use things like glass though, and there are other types of materials that are more useful in that case. This is an interesting picture here showing induction cooking. There's a piece of chocolate, a chocolate bar, with a half pan. Only the chocolate in the pan is being cooked. The chocolate on the other side of the stove is not being cooked. And you could place your hand on top of the surface, although it's not advised that you do that because that is kind of dangerous if you do touch it. Metal detectors use electromagnetic induction as well. So what they do is they use a magnetic field to induce a current in any metal that might be near. If they induce this current, the metal detector then can measure that the magnetic field that the current is induced by, and then it can determine that there is some sort of metal device underneath the wherever you're searching. So metal detectors have many uses for humanitarian purposes, security reasons. Hobbyists use them as well. Loggers use them. Induction chargers can charge phones or tablets or other electronic devices without having to physically connect. They can basically induce a current in the internal battery of the device to charge that device. So you won't need those wires. You won't need to kind of look around for things. You won't get frayed wires. You can have a single charging station for several devices. So here's your last slide to copy down. The applications of electromagnetic induction. We have generators, transformers, induction cooking, metal detectors, induction chargers, and there could be a few others, but that's all you need to know for now.